Working with vector space R3, we have three vectors u1, u2, u3 given for us. They are given to us, and we need to check the three vectors u1, u2, u3 is an orthonormal basis for R3. So there's two things, in fact. Is an orthonormal set, and this set is a basis for R3. Okay, so the first thing we talk about orthogonal set, orthonormal set. So we need to show that u1, u2, u3 is an orthonormal basis for R3. So recall that orthonormal set is a set, the vectors in the sets are pairwise orthogonal, and they are on unit vectors, right? So for the first condition, orthogonal, we need to check that the inner products for the first condition, we need to check that the inner products of ui and uj equal to 0 for I different from j. So u1, we need to check inner product of u1, u2, u1, u3, and u2, u3 are on 0. So this is the first step, orthogonal. Second step, we need to check their own unit vector. This means that we check norm of u1 equal norm of u2 equal to norm of u3 equal to 0. And recall that norm of ui, or norm of u1, is the square root of u1 inner products with u1. In our case, the inner product is just a dot product. So it's just square root of the dot products of u1 dot u1, right? So for example, if u1 is given to us like ABC, then this is just square root of, which is square root of a square, b square, c square. Okay, so we just need to check the two condition, orthogonal condition. Check, compute the inner products of the three vectors u1, u2, u3. They are vectors of length 1, and then we have an orthonormal set. And since we need to check this is a basics of R3, so recall that u1, u2, u3 is orthogonal. Then we did prove that u1, u2, u3 is linearly independent, and they are three vectors linear independent in R3. Vector in R3, therefore it is equivalent to, its also span to R3 is equivalent to this form a basis for R3. Okay, therefore we don't need to check the span condition or linear independent condition because of this theorem. That's orthogonal sets must be linear independent. Okay, so for the first part, we just need to check the vectors are orthogonal and the vectors are unit vectors. And for the second part, write x as a linear combination of vector in u1, u2, u3. Okay, now we use a theorem we proved before. So theorem 1 here. We will use this theorem. Recall that V is an inner product vector space. So a vector space with inner products. In our case, it's R3 with dot products. We have the set of 3 vectors so our u1, u2, u3 orthonormal set. We have that. So if any vector v in the vector space big V can be written as linear combination of the 3 vectors, and this linear combination has a coefficient can be determined by the inner product of V with the vectors in the orthonormal set. So in our case, we have we have R3 inner product vector space. Actually, this is, we use the dot products. We have 3 vectors, u1, u2, u3, orthonormal set. In fact, stronger orthonormal basics for R3. And we have any vector v. In this case, we have they said x. Okay, we use the notation x. Any vector x in R3. We want to express x as linear combination. Say C1 of U1 plus C2 of U2 plus C3 of U3. And we want to find this explicitly the linear combination. All right. So using the theorem theorem 1, we just said here, we have C1, C2, C3 can be determined by C1 is the inner product of X with U1. Right. C1 is the inner product of X with U1. C2 is the inner product of X with U2. And C3 is the inner product of X with U3. Okay, so let's look at our exercise. In our case, X is, so in our case, X is, say, a vector 1 on 1, right? Is vector 1, 1, 1, transpose. So U1 is, in our case, this is 1 over 3 root 2, 1 over 3 root 2, and minus 4 over 3 root 2. Okay, so here we can use this. So we have X, we have U1. When compute the inner products of X and U1, then this is C1. Right? It is just the dot product of the 2 vectors. So 1, 1, 1 transpose dot products with this vector. You transpose here. And what is this? 1 times 1 over 3 root 2 plus 1 times 1 over 3 root 2 plus 1 times minus 4, 3 root 2, right? So this is 2 over 3 root 2 over 3. Yeah, so this is from the first case, right? This is for C1. And we do C2 and C3 similar. Yeah, so that is the first part of part 3, part B. And we use the Parseval formula to compute the norm of x. So similarly, we can compute C2 and C3. And we get this x equal to this form. And then we get explicit values C1, C2, C3 here, right? And now use Parseval formula. Recall that the Parseval formula, okay, we will state the theorem explicitly. So this is the Parseval formula that we proved before. So the Parseval formula said that if we have an inner product vector space, in our case it's R3 with the dot product, we have 3 vectors orthonormal set. We have in R3, we have vector V, in our case vector X, linear combination of 3 vectors U1, U2, U3. Then the norm of vector X square. So Parseval formula said that the norm of vector X square is the sum of all coefficients square. So in our case, we have norm of x squared. By Parseval formula, we have it is the sum of x1 squared, c1 squared plus c2 squared, c3 squared. Remember that we compute c1 explicitly, this root 2 over 3. Right, c1, I'm sorry, this is minus root 2 over 3. C1 is minus root 2 over 3, so minus root 2 over 3 square. Plus C2 you compute explicitly, C3 you compute explicitly, and you get the answer. Something. And we're done with the exercise.